right, welcome back. Physics 12. We are talking about electromagnetism a bit more today. Last week we were talking about the magnetic fields that are created on a single wire. That's where we had the right-hand curl rule, or right-hand rule number 1, where if we curl our hands kind of like into a fist, then our fingers would tell us the direction of the magnetic field, and our thumb would tell us the direction of the current in the wire. And we also talked about how we can determine the direction of force on a current carrying wire if it's in another magnetic field, or how the magnetic field from the current carrying wire interferes with other magnetic fields and can cause a force on the wire. And that was our right-hand rule, where we had our thumb representing our force, our index finger representing the current, and our 3 other fingers representing the direction of the magnetic field. So today we're going to change it up a little bit. It's very similar in concept to what we talked about last week, but now we're talking about having a wire that's in a coil. So when we looked at the current carrying wire last week, we saw 2 scenarios. Remember, we drew the magnetic field going into the page as an X, because it looks like when you fire an arrow away from you, you can see the tail feathers of that arrow. That's why we draw that symbol here for current going into the page and current going out of the page. And if we were to use our right-hand rule, say for the current coming out of the page here, if our thumb is pointing out of the page and we curl our hand around it, or we curl our fingers around, our fingers are going to tell us the direction of the field, like this. And likewise for a wire going into the page, if we point our thumb towards the paper and we curl our fingers, then the magnetic field is going to be clockwise around a wire that's going into the page. Now, this may be interesting. You may find it interesting. It has limited uses. It's hard to actually cause an interaction with a magnetic field, especially if it's just one single wire. The only way to get more current is the only way to get a stronger field is just keep pumping more and more current into it. But eventually, it's costly and it can melt the wire, etc. So how would we create a stronger magnetic field around a piece of wire? And how could we make a magnet go in one direction as well? Instead of being a circular path, what if we wanted our magnet to be more like a straight magnet, where we have something like this? So in a normal magnet, we would have our magnetic field go something like this, in this direction, going from north to south. Well, we can do that by creating a coil of wire. And a coil of wire has another name, fancy name, which is a solenoid. So a solenoid looks something like this picture here on the right. Now, what I've done for these circles on the left, if you're curious what that is I've essentially cut this in half. So if I could somehow cut this wire in half and we could see right down the middle. So what we have here, for example, this wire is coming in from the left-hand side and goes down here. And so at the bottom, it's going into the page. And then as it comes around the top, it's now going to be coming out of the page. Goes around the bottom, goes into the page, etc., and comes out of the page, out of the page, out of the page, etc. for here. So if we were going to cut this wire in half, cut the solenoid in half, this is what we would see as a cross section. Now, what I want you to think about, and if you want to pause the video and try drawing this for yourself, is what would the magnetic field like when we're combining a number of these loops together? Well, so feel free to pause the video if you'd like to try drawing this out for yourself. And if you already have paused the video and you come back, or if you're just not interested in doing that, that's fine. We'll take a look at the field anyway. So what I want you to think about is, for each of these individual wires, we know that when it comes out of the page, it has this counterclockwise pattern here. So if we were going to draw the magnetic field at different points, it would look like this, and like this, and like this for the first wire. And likewise for the second wire. I don't really want to draw it going through these other pieces of metal, so I'm just going to include it this way. What's happening above and below the wire for each of these individual sections of wire. And then this would be like that. Now, likewise, when it's going down into the page, like we have up here, it's going to be clockwise. So we're going to have it going up and in, etc. for all of these. And on the bottom, it would be going this way. Okay, so this leads us to our second right-hand rule. So what you can see, and I'm going to show you a slightly better drawing that I've drawn here. So this is just the idea of where this shape comes from. But let's take a look over here. This is another picture of a solenoid, or a cutaway of a solenoid, and we can see the direction of the magnetic field. Now in this case here, I think I've drawn it in the same direction here. So this is at the top, we can see the dot, so it's coming out of the page over here, and it's going into the page at the bottom here. Same thing as the drawing that I've done on the left, and these are coming out of the page. And we can see overall, if we take a look at the shape of this magnetic field, you might notice there's a slight difference between the outside and the inside of the solenoid in terms of the overall shape and kind of consistency of the magnetic field. So I want you to think about that. Last week we talked about how the Earth creates its own magnetic fields. And so this is kind of giving you another idea of this. In the mantle of the Earth, there is going to be these large convection currents that are moving around. And these convection currents are essentially, they act as if they were a coil. And so we get these magnetic fields being produced by circling convection currents in the magma of the Earth, in the liquid core, not the solid inner core, but the liquid outer core. And so we can see it creates these solenoid type activity as well. So you're going to get these magnetic fields being produced from that. So this leads us to our second right-hand rule. And essentially, it's easy to remember, it's the exact opposite of the right-hand rule we had for current. So remember when we had a single piece of wire, our thumb was pointing in the direction. So in this case here, if I have my thumb sitting over top of the wire pointing out of the page, my fingers are going to represent, so my fingers here represent the magnetic field, and this thumb represents the current. If we look at a solenoid, well, let's see what happens if we put our fingers in the direction of the current. So if I have my fingers coming out of the page here, so let's imagine that my four fingers are acting like the coils of this wire. So at the top here, the coil is coming out of the page, and at the bottom, coils are going into the page. Now, if we try and line our fingers up so they match with that, then if I curl my right hand up so that my fingers are pointing out of the page at the top, and then if I continue to kind of rotate my hand more towards me, my fingers would eventually point downwards into the page here. Well, look what direction my thumb is going. My thumb is going, in this case here, to the right. So my thumb is going to be going in this direction, which is also the direction of the magnetic field, and my fingers are going to be going in this direction, which is the direction of the current. So here, the current was our thumb, and the magnetic field was our fingers. Now, the current is my fingers, and the magnetic field is my thumb. So we've reversed that for the second right-hand rule. So again, the fingers here represent the current, and the thumb represents the magnetic field. Just use B for shorthand for a magnetic field. So just a quick note and a reminder, when we are using the right-hand rule, we're always going to be looking, so when using any right-hand rule, we have to remember that we are using the conventional current. And remember, when we consider conventional current, what we're really talking about is this idea that in a circuit, positive charges are moving in the direction of current. Now we know that in real life it's actually electrons moving in the opposite direction, and for reasons we'll get into next week, it doesn't matter. So we can consider this as conventional current, and the rules will be absolutely correct. If we wanted to use the movement of negative charges, we would just use a left-hand rule for movement of negative charges. And what you'll find is that if you think about negative charges moving backwards, you'll still end up getting the exact same direction of magnetic field if I use my left hand here. And this works no matter what right-hand rule you're using. If you use the left-hand rule, you're talking about negative charges moving backwards, right-hand rule, positive charges moving forward. And just as in a bar magnet, solenoid does have it has north and south poles. So in this case here, if we look at this direction here, this would be my north pole, and this would be my south pole. So the north pole is where the field lines come out of, and the south pole is where the field lines go into. So just like this one here, north and south. Or this one here, north and south. So all these solenoids are drawn the same way. And so all we're doing for this right-hand rule is just flipping the direction around. So our fingers are the direction of the current, and our thumb is the magnetic field. Now, if we take a look at this diagram up here, what you'll notice is that on the outside of the solenoid, the field is going to be, relatively speaking, weak and non-uniform. So, closer to it, you can see these are closer together. As you go further out, you can see that it's more spread out. You can also see that if I look here versus here, there's a difference in how far apart the field lines are spread. So it's not uniform outside, but if we take a look inside here, it's quite uniform. We've got all these parallel lines. They're all pointing in the same direction. They're all relatively evenly spaced out. So inside these coils, the magnetic field is, first of all, it's stronger because they're all close. You can see they're packed much closer together, and it is uniform. Okay. Oh, sorry, I was using the wrong lines here. So the field line here is stronger, and the field is uniform. Okay. And so this part here, they're weak and non-uniform, especially if its width is much greater than its length. So if you've got really wide circles and a very short solenoid, so wide as in this side here, and short as in this dimension here. Okay, so we do have a formula for determining the magnetic field strength, but that formula only applies inside the solenoid. And that formula is as follows. B, the magnetic field, equals mu naught times I times N. So this is the magnetic field. Obviously, we've seen this before. Now this mu naught, this is called the permeability of free space. So you can think of this as one of our universal constants. So for example, just like big G is a universal constant, 6.67 times 10 to the minus 11, or we have K, kind of a universal constant, or it's related to another universal constant. This is 9 times 10 to the 9. Mu naught is another, it's another unit here as well. So it's just another universal constant, and it equals 4 pi times 10 to the minus 7. So if you calculate what that is, if we have, let's see, pi times 4 times 10 to the minus 7, this gives us about 1.26 times 10 to the minus 6. Okay, so this is a universal constant, just like big G, for example. I, of course, is the current in the loop, and N is the number of coils per unit of length. So this N is basically telling you how closely packed they are together. So if I'm counting the loops, I might say this is 5 loops, and this is 1 centimeter, and so N might be 500 loops per meter. Okay, so this is a number of coils per unit length. This is also sometimes written as N. So N is the total number here. So this is total number of loops divided by length. That would be the length of the solenoid. Okay, so let's try this first question here. So give yourself a moment, pause the video, and then try and answer this question where we have a hollow solenoid, 25 centimeters long, with 1,000 loops, diameter of 4 centimeters, current of 9 amps. What's going to be the magnetic field? So try giving that a shot and pause the video and come back when you're done. Okay, so hopefully you have tried this out. Let's try solving it ourselves. We're trying to find the magnetic field. We're trying to find B. We already know that this is our formula here. B equals mu naught times I times N. So we don't need to rearrange. So this is going to be our formula. This is the same thing as saying mu naught times I times N over L. That's what N is equal to. And in this case here, this is going to be approximately 1.26 times 10 to the minus 6 multiplied by 9 amps multiplied by 20, it's going to be the number of loops. So 1,000 loops divided by 25 centimeters. We know that's going to be 0.25 meters. So let's take this value that we got here. We're going to multiply that by 9. We're going to multiply that by 1,000. And then we're going to divide that by 0.25. And that's going to give us this value here. So B equals 0.045. Let me just check for sig figs. Yeah, 0.045. And the unit for magnetic field strength is Tesla. So a solenoid is essentially a coil of wire. If we want to know the magnetic field strength inside, this is the formula we're going to use. What do we use these for? What exactly is a solenoid? What's the purpose of a solenoid? And a solenoid is essentially, they're used to make electromagnets. Now, an electromagnet is a way of getting a much stronger magnetic field than we can from just natural magnets. So the strongest natural magnets you can get are neodymium magnets. They're called rare earth metal magnets. And the maximum strength you can get out of a neodymium magnet is around 1.4 Teslas. Now, if you're talking about electromagnets, they can run the range. The world record is about 1,000 Teslas, but those only last for a tiny fraction of a second before they explode. If you want to check out a cool video, Google Japan lab strongest magnet and watch the video. It's a magnet that they got to work for a tiny fraction of a second, and it blew the doors off this very secure lab. So kind of a cool video to check out if you want to. But the strongest ones that are kind of permanent, that can not destroy themselves essentially, are around 11 to 13 Teslas. An MRI, and I'll show you a cool video here, an MRI typically has a magnetic field of about 3 Teslas. So just to give you an idea how strong 3 Teslas is, let's check out this video. And so you can watch the whole video.
So the force we're reading on that guy right now, just at that part of the magnet, is close to 300, 280?
Yeah, pretty good. Let's see what we can get.
That's measuring it in pounds. So essentially the force on here would be the same amount of force as a 300-pound person standing on your hand, for example.
That guy.
No.
400 now.
And it's going to attach itself to the board here in a second.
Any second it's going to start dropping here. Gravity will just do enough.
There it
There
goes.
it goes. Oh, that's almost 600.
Now it is giving us a reading of 500 pounds.
500 pounds of force pulling on that magnet in that magnetic field. So these are incredibly strong magnets. Now so these are called electromagnets. We can make them incredibly strong. Now the 4 ways that we can strengthen them are often called just the 4 C's. So take a moment and see if you can think about what some of those C's may be. So what are the ways that we can make an electromagnet stronger? Take a minute, think about that. And hopefully you can think of a couple. So a couple of them that are maybe the more obvious ones. More current. So more current, you're going to have a stronger field. Also, coils. If you have more coils in your loop, you're going to have a stronger magnetic field as well. You can also put these loops closer. These are closer loops. The more densely packed you have them, the stronger your magnetic field is going to be. And the last one here is a core. So having an iron core. So what that means is if I have my solenoid and I put a iron bar or something that can be turned into a magnet, if I put an iron bar in there, what that does, because I've got my own magnetic field from the coil, let's say the magnetic field is going this direction here. Okay, so I've got this magnetic field in the coil. Well, what that does is that turns this magnet into a magnet itself, or that turns this iron bar into a magnet. Remember that these iron bars are full of these little domains where all the magnetic fields are pointing in different directions. However, when I put this in a magnetic field, all of these individual domains of the magnet are also going to end up lining up the same way. And so what that does is it strengthens the magnetic field. If you have an iron bar inside of a solenoid, it just turns that iron bar into a magnet, which adds more magnetic power to the solenoid. So this is a way that we can make electromagnets even stronger. These 4 ways: bringing more current, bringing more coils, bringing the coils closer, and adding an iron core. Okay, so when we're talking about this unit, it can be a bit confusing because essentially both of these ways that we deal with current, it's a reversible phenomenon is what I'm trying to say. So what I mean by that is we saw last week that if we put current in a wire, that creates a magnetic field. So if we're forcing these charges to move down the wire, we're applying a force to these charges, we're putting a potential difference in a wire, we're essentially applying a force to push these electrons or push these charges down a wire, that creates a magnetic field. We also saw that when we have a wire in a magnetic field, then that applies a force on the wire. So these things can affect each other in both ways. What I'm trying to say is if we look at what we've done so far in this lesson here, we have seen if we apply a current, we can make a magnetic field in a solenoid. But now the question is, what if we apply a magnetic field, an external magnetic field to the coil? What we're going to find is we can also create a force. So if we apply a current, essentially we can get some kinetic energy out of it, and if we apply if we apply a current, we can get a magnetic field. If we apply a magnetic field, we can also get the reverse happening. We can get a force back in a sense. So let's see if I can explain that a bit better. If we have a wire inside a coiled magnetic field, the total length of wire that we would use to determine L is just the length of one loop multiplied by the number of coils. So the formula for a coil of wires would be, we saw this formula last class, F equals B/L, or F equals Bill. Remember, this is the magnetic field, the current, and the length of wire. So if we have a number of different loops, then we're just going to have BIL times N. So this is the force on a single wire, B times I times L, and we're going to multiply that by number of wires, which is our capital N. So capital N is number of wires, lowercase n is number of wires per meter. Okay, so what if an entire coil was inside of a magnetic field? How would we determine what the force is on the sides of that? So to make our life a little bit easier, we're going to assume that the coil of wire that we're going to use is a rectangular coil. So I'm going to try and draw that out for us here. So let's say I have got a coil of wire that looks like this. And we're just going to have to assume that there are a number of coils here. So this isn't just one loop of wire, this is N wires that are all lining up on top of each other. So there's another wire, another wire, another wire, etc. So we've got a loop of wires, there's N wires, and I'm going to call this dimension here W for the width, and I'm going to call this dimension here L for the length. Now we're just going to imagine that there is going to be an invisible line down here where this is essentially attached and free to rotate. So this coil can rotate around this red line. This is our axis of rotation. Now let's assume for a moment as well that we have a magnetic field that's moving in this direction here. And let's also assume that our current is going, in this case, counterclockwise. So our current is going to be in this direction here. The green line here represents our magnetic field. Because it's a loop, the current's going to be going in this direction on the other side. So the current's going counterclockwise around this loop in the magnetic field. And what I want you to think about is what direction are the forces going to be on this point here. So for force, let's use black. So what direction would the force be on this wire here, on this wire here, and on this wire here, if any? So please, at this point, I'd like you to pause the video, and I'd like you to think about using the right-hand rule. So ignore everything else. Let's just look at one wire at a time. So let's look at the right-hand side of this, and we've got a current going in this direction upwards. We've got a magnetic field going to the left. So what direction is the force going to be on this portion of the wire here? So pause the video here, and I want you to determine what the directions of force are going to be on these four sides: top, bottom, left, and right. All right, hopefully you are back after you've paused the video. We just did a quiz last week on directions of force, so this is old information for us. We're just applying it in a new context. So in this case here, if I use my right-hand rule for the right-hand side, I've got my current, or my index finger, pointing upwards. I've got my magnetic field, or my other three fingers, pointing to the left. And so what direction is my thumb moving? Well, my thumb is moving out of the page. And for that, we signify that with a dot. On the right-hand side, on the left-hand side, I should say, my finger is going to be pointing downwards, my index finger is pointing downwards, my three fingers are still pointing to the left, and so my thumb is going to be pointing into the page. And so we're going to have a direction going into the page on the left-hand side, out of the page on the right-hand side. Now what you'll notice is, for the top and the bottom, the current and the magnetic field, these are going to be parallel. And when the current and magnetic fields are parallel, then there is no force. So no force on the top or no force on the bottom. So I'm just going to erase those two circles here. There is no force at the top or the bottom. Okay, so we've got that information about the coil. And we can see here that if I was to put along this red line here, if I was going to put some bar, some attachment, some axle on this coil of wire, then you can hopefully see that this is going to rotate. The left-hand side is going to want to move out into the page. The right-hand side is going to want to move out of the page. So you'll see that it will start to rotate around this red line axis right here. So let's try and calculate what that force is going to be. So we're going to run through some derivations here. I would strongly encourage you, try solving this for yourself. You may get stuck, so feel free to pause and restart the video as we go. But a lot of these formulas we've seen before. So first of all, we do know what the torque is going to be. We've seen this formula here. So the torque produced is our force multiplied by our distance. And we also know our formula for force on a wire or on a number of wires. So if we're looking at the right-hand side, we know that the force is going to be B times I times L, the length of the wire, times N, the number of coils. Now, what about our distance? So if we want to figure out the force times the distance, well, what is the distance? Well, the distance is going to be W over 2, but I'm going to add something here, which is cos theta. Now, what exactly is this cos theta? So if we take a look at this picture right here, we can see that this coil is going to go into the page, and this coil here on the right-hand side is going to come out of the page. So what is that going to look like after it's had some time to rotate? Well, a little bit in the future, it's going to look something like this when it's free to rotate. Okay, so it's had some time to rotate, and it's going to look something like this here. So this left-hand side has moved into the page, this right-hand side has moved out of the page, and this angle here, this is our theta. So if we look at this from the top, this is what it's going to look like from the top. So now I'm looking at viewing it from this direction here. So if I'm viewing this from the top, this is what it's going to look like. I'm still going to have my magnetic field going to the left, but this coil of wire is now going to be from the top, it's going to look something like this from the top. So originally it was in this direction here, but now it's going to be in this direction here, and it's moved by this angle here, theta, or that angle there, theta, same angle there. And at this point here, the current's going to be going into the page. So the current's going to be on the left-hand side going downwards. We're viewing it from the top, so it's going to look this way for the current and this way for the current. And the force that we're going to get is going to be, well, if it's going down into the page here, and the field lines are going to the left, and my index finger is pointing down, field going down, or field going into the page, sorry, current going into the page, field going to the left, it's going to look like this and this for our force. So this is our force, this red is our current, and this green is our magnetic field. Okay, hopefully that makes sense. And if you need to pause the video or reset it, set it back a few seconds, that's fine, just to make sure that you understand what this is. So this picture on the right is just looking at this from the top-down view, so looking at it from this angle. Okay, so what is the distance here? So if this is the point we're looking at here, if we're trying to find the distance where the force is acting, remember we have to find the perpendicular distance when we're talking about torque. So that's going to be what we're looking at here, which is going to be W over 2 multiplied by cos theta. So this part here is W, this would be W over 2, and this distance here would be W over 2 times cos theta. So that's where this distance comes from. Okay. Hopefully we followed along with that, and if not, again, feel free to rewind it and head back and try this again. So now we're going to put all this together. So we know that if we're looking at one set of wires, let's look at the left-hand side here. The total amount of torque is going to be force times distance, where my force is going to be BILN, and my distance is going to be W over 2 times cos theta. But now, keep in mind that whatever force or whatever torque is acting in this direction. So from this angle here, from the top-down view, I would call this a clockwise torque caused by this force at this distance. And this would also be a clockwise torque, and it would have the exact same amount. This force is also going to be BILN. It's also going to be at W over 2 cos theta. So in this sense here, we have two torques that are both clockwise. So we're going to take this, if we want to figure out the total amount of torque, so the total amount of torque is going to be the torque from 1, which is BILN, times the distance, which is W over 2 times cos theta, and we're going to multiply that by 2 because there are two torques that are both acting in the same clockwise or counterclockwise direction, which means we can cancel these out. Now, this is one way of writing it. One way that we can simplify this a little bit more, one step more simplified, is think about what L times W is. So if this is W going across here and this is L, what would the product of those two things be? What would be the product of the length times the width of a square? Well, hopefully we know what that is. The length times the width would give us, I'm just going to simplify this a little bit here, B times I times N. I'm going to multiply that by length times width. Well, what is length times width? Length times width is the area of that square. We're going to multiply that by cos theta. So when theta is equal to 0, that means that we're in the starting position here where the direction of the current is completely parallel to the direction of the magnetic field at the top and bottom. And if that's the case, we have BIAN or BINA times cos theta, and theta of 0 degrees is 1. So at the position where it's flat, here, flat on the page like we started with, then the total amount of torque here is going to be BIAN. And if it's at 90, what's the total amount of torque going to be? Well, let's imagine this scenario here, but where they're acting at 90 degrees. So here is my magnetic field. Here is my loop. So now this loop has the current coming out of the page at the top, and it's going into the page at the bottom. And what is going to be the direction of force for both of these? Well, it's going to be the same as before. If the current's going into the page, magnetic field's going to the left, the force is going to be going upwards here, and it's going to be going downwards here. So what is going to be the total torque in this scenario here? And hopefully, by looking at the picture, you will recognize that the total amount of torque here is going to be 0. These two forces are not going to cause this loop to rotate. They're going to try and stretch the loop out, but they're not going to cause it to rotate. If we look at this top situation here, these two forces are definitely going to cause it to rotate. In this situation here, they're not going to cause it to rotate. We also know that cos of 90, so that's going to be this angle here, cos of 90 equals 0. So mathematically, we know it's going to be 0, but also from looking at the picture, we can see that there's not going to be any torque in this scenario here. Okay, that is our lesson for the week. Hopefully you found it educational and informative and maybe entertaining or interesting at the very least. If you have any questions, please come by the Fit Block on Wednesday at 1. All right, see you then. Thanks.